Hello, everyone. Welcome to the Audio Precision webinar. Today, we'll be discussing open loop audio test with Joe Bajin, who will be leading the conversation and providing demonstrations on APX 500 software. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items before we get started. First, please note that this webinar is being recorded. A recording of the session will be available to you beginning of next week, so be looking for an email in your inbox for that. Secondly, we welcome questions throughout the presentation via chat in Microsoft Teams. So you should see a chat icon in the upper right or upper left corner of your screen. And most questions will be answered at the end of the presentation, at which point we will be doing Q&A. Joe has a lot of information to share with you today, so without further ado, Joe, I turn it over to you.
All right, thank you, Paige, and thank you everyone for joining our webinar today. So Paige, are we sharing my screen at this point?
Not yet. Let's see. We're still sharing my screen. Can you open your share tray?
Yeah. Is that coming up now?
Yes, now it's there.
Okay, great. All right, thank you, Paige, and thank you everyone for joining our webinar today. I'm just going to drag this little piece off the screen so that doesn't distract you. And yeah, so we have a lot of material to cover today, and I'm just going to jump right into it. So our agenda today, we're going to have a little discussion about open loop audio measurements and talk about some of the devices that require this type of audio test. We're going to cover the basic audio quality tests, and then we're going to do some demonstrations, a playback device test, and then a recording device test, which will involve some acoustic measurements. And at the end, a little bit of time for reviewing questions. All right, so first some definitions. What do we mean by closed loop audio test versus open loop audio test? So in a closed loop test, the audio analyzer works in concert with the generator. So first, a pure signal is generated by the audio analyzer and input to the device under test, or the DUT. The output signal from the DUT is instantly acquired by the audio analyzer. If there's any delay, it's usually quite minimal, and that's removed, the delay between the input and the output. The audio signal is generated and analyzed in one continuous operation. And then the output signal is analyzed to determine audio quality metrics such as level, gain, distortion, phase, frequency response, and so on. Now, here are some of the audio devices that can be tested in a normal closed loop configuration. Of course, power amplifiers, audio converters, digital to analog converters, analog to digital, and sample rate converters, audio interfaces, loudspeakers, microphones, hearing aids, communication networks, and basically any device that immediately passes audio. In an open loop test, the audio signal is not passed through the device and analyzed in one continuous operation. And this could be for a variety of reasons. So one reason might be that the signal does not originate, or the signal might originate as a file on the device under test. And this would be the case for a media player like a smartphone or a tablet or a Blu-ray player. The signal may originate as a file on a server connected to the DUT, and this could be the case for a smart speaker or a Wi-Fi speaker or a set-top box. Or in the case of a recording device, the device may not output audio at all. Rather, the signal terminates as a file on the device under test. And an example of this would be an audio recorder, a camcorder, or a PC sound card. And in another case, the signal from the DUT may terminate as a file on a server. And this would be, for example, the command function of a smart speaker, its microphone function, or a remote voice recorder. So some examples of devices that have to be tested in an open loop configuration. First, we have media players. This could be something like a turntable that plays vinyl records, disc players, Blu-ray, DVD, CD, etc. A car head unit where you're playing the signal off a USB flash drive, and PCs and tablets and smartphones. So PCs, tablets, and smartphones are kind of special because they show up in many of these categories because they have so many different functions. Another example is media streaming devices. So this could be set-top boxes, Wi-Fi speakers, and again, our category of PCs, tablets, and smartphones. Integrated circuits. So you may have a chip with embedded audio. One example might be a smoke alarm or a fire alarm where there's an embedded chip that has voice prompts to tell you to leave the area because there's a fire. So in the case of these devices, a high quality audio test signal must be placed on the source medium that's being played or on the device itself. And in many cases, this can be created by an audio analyzer. But in the case of a vinyl record, for example, you can't just create a vinyl record. You have to buy a test record. And chances are that if there is a test record, you can use it with the audio analyzer. So in this case, the audio analyzer measures the signals played back from the device under test. Now for audio recording devices, some examples are digital audio recorders, video recorders, audio interfaces, PCs, smartphones, and tablets. And in this case, a high quality audio test signal generated by the audio analyzer is recorded on the device under test. That recorded file is transferred to the audio analyzer for analysis. Another example is the voice command function of a smart speaker. So smart devices, smart speakers and smart devices have two audio paths. The primary one is the audio streamer, where the device plays the content that we've requested. But the secondary one is the voice command path. And the voice command path is somewhat like an audio recorder. So here you can use an audio test signal that you prefix with the wake word. The wake word being a word like Alexa, or in the case of Google, Hey Google, a word that is recognized by the device. So you generate the audio test signal containing this wake word. And with support from the intelligent virtual assistant, a digital audio file of the recorded command can be retrieved and analyzed. So for example, if you've used the Alexa service, you can log into your Alexa account and look for recordings of these commands that you've made to the Alexa device with a timestamp on them. Now this probably requires a speech stimulus because many of these devices have DSP inside them that prevents passing things like sine waves and noise. And in this case, you can't use a sine signal to test the device, so you probably want to use a speech stimulus. Another application for open loop test is broadcast. In this case, we have a transmitter and a receiver, and they're separated by some large distance. Now, to inject a signal into the transmitter, we could use an audio analyzer at this end, and to acquire the signal from the receiver end, we could use an audio analyzer at that end. But because the devices are separated by such a large distance, it has to be an open loop test. Moving on to audio quality metrics. So at Audio Precision, we like to think of the basic 6 audio quality metrics. And these are the measurements which are built into the sequence mode of our APX analyzers. So these are level and gain, harmonic distortion, signal to noise ratio, crosstalk, interchannel phase, and frequency response. And of course, there are many more, but today we're just going to focus on the basic 6. So a classic means of doing audio test is with sine waves. We like to use sine waves because they're very simple. We have a periodic waveform, and looking at the frequency domain, this is an FFT plot, and you can see all of the energy appears at one specific frequency in the spectrum. And you can see here, using an FFT analysis, we can get a good idea of the signal to noise ratio just by looking at the value of this peak relative to all of these, all of the noise down here at the bottom. We can also see some tiny harmonics peeking through. This is a very pure audio signal generated by our APX 555 audio analyzer, which happens to be the one that I'm using today. So we take our pure sine signal, we pass it through the device under test, and we acquire what comes out the other side and analyze it and compare it to the original. So you can see here in the time domain, we get some small ripples on this sine wave, but you can really see a lot more in the frequency domain with this FFT analysis. So in addition to the fundamental, which went in, we get a series of harmonics and noise. And with this sine wave, we can determine many audio quality metrics. We can look at the level, we can look at the gain by comparing the level of the what comes out to the level of what went in. We can determine the frequency, and we can also determine harmonic distortion. So for harmonic distortion, what we do is we take away the fundamental, and everything that's left consists of the harmonics and the noise. And we sum up the harmonics and the noise and express those as a ratio of the total signal. And that's the classic audio quality metric called THD plus N for total harmonic distortion plus noise. Now, the open loop test procedure for a playback device, or the playback function of a device that does both record and playback, looks something like this. So for example, suppose our DUT is a smartphone that we're going to use for playback. So first we configure the signal generator in the audio analyzer. We create a wave file of a pure signal. And to play it from the device, we may have to encode it. So some devices can't play wave files directly. They have to play, for example, an MP3, or it could be a video file. So we may have to encode the file. We upload the file to the device under test or to a connected media server. We start the analysis in the APX software. We play the file, and the analyzer acquires the signal and analyzes it. So we're going to do a little bit of a demonstration here on a device in an open loop configuration. And my device today is the sound card of a PC. So I have a laptop on my desk, and I'm looking at the analog output of the laptop. Of course, it's stereo, so I have two channels connected. And I have cables going from the analog output to the unbalanced analog inputs, channel 1 and 2 of the audio analyzer. In this case, I'm not using the generator section, so I've just crossed it out here. And as a kind of an auditory aid, I've also routed the signal through an amplifier and some monitor speakers that I have above my desk here. So you'll probably be able to hear the sine signals as we play them. Now this is a graphic of the analyzer I'm using today. It's our APX 555. It's our top of the line instrument, so it's really overkill for this application, but it's one that I happen to have on my bench. And these are all the digital modules that we have, which I will not be using today. It's strictly an analog demo that we're doing today. All right, so let's bring up the audio analyzer software. So I have it running here in the background. And this is what the software looks like when you open it from scratch. So you get a blank project, we call it. It has one signal path. And inside the signal path, it's pre-populated with 6 measurements. And they just happen to be the basic 6 audio measurements that we're talking about. So level and gain, THD plus N, frequency response, signal to noise ratio, crosstalk one channel undriven, and inter-channel phase. So before jumping into the open loop test, I just want to demonstrate some things that make a closed loop test very easy. And to do that, we have this little checkbox here called loopback, and this routes the signal from the generator internally back to the analyzer. And the only other thing I'm going to do is change the bandwidth down to 22.4 kilohertz. That's the standard audio band. And now with a closed loop test, we have this section down here where you can verify connections, and makes it very easy. You can just kick on the generator. By default, we're generating a signal that's 100 millivolts RMS at 1 kilohertz. And as you can see here, I'm getting a signal on channel 1 and channel 2. And if I switch the test channel from channel 1, you can see that I just get a signal on channel 1 with nothing on channel 2. Similarly, if I generate the signal on channel 2, I only get a signal on channel 2 and nothing on channel 1. So having the closed loop configuration makes it very easy to conduct the test, to see what's going on. And then, of course, for measurements like level and gain, the analyzer can easily recognize a sine wave coming in, for example. So that's quite easy to do open loop. When we get to measurements like signal to noise ratio, it's a little bit more complicated. Now in this measurement, I specify a frequency and a level. And when I press the start button, the system will turn on the signal, measure the level of the signal, turn off the signal, measure the level of the noise, express the ratio of the two, and show that on the display. So that's a very quick operation, open loop. And as you'll see, when we go to do it, sorry, closed loop, it's a quick operation. When we go to do it open loop, it's a little bit more complicated. So let's go back to signal path setup. And I want to configure my system here for an open loop test. So as I showed in the slide, I'm not using the generator. So I'm going to set the output connector to none external. And that means the analyzer is not generating a signal. It's expecting a signal to come from the device under test. Then on the input side, I have a choice of input connectors corresponding to all of the digital modules and the analog inputs I have. And I'm going to choose analog unbalanced because the outputs from my PC sound card are connected to my analog unbalanced inputs. Now that I'm ready to test, so right here, I'm looking at the incoming spectrum from the device, and I actually have the laptop hooked up at this point, and as you can see, I'm getting some noise. I have some 60 hertz hum here at about 20 microvolts and some harmonics of that, and then just some noise on the noise floor. So let's next, what we're going to do is set up the device under test. So what I've done here, I have a remote desktop connection connected to this laptop, and I need to play some pure signals from the laptop. So we have a nice tool for that. It's called the APX Waveform Generator Utility, and I have it in this little folder. It's quite a light application. You can download this from ap.com. It's called the APX Waveform Generator Utility. And you may not be able to see here, but the size of this application is just under 7 kbytes. So it's quite small and small download, and it's quite useful. So we just double click it to open it, and we get a list of parameters here. So first is the sample rate. We have all the standard audio sample rates built in from 8K to 432. I'm just going to go with the default of 48K. I'm testing a stereo device, so I'm going to pick 2 channels. The resolution or bit depth is shown at 16, 20, 24, or 32. I want to use the default of 24 bits, and then I have a list of files that I can generate to use for open loop testing. And I'm going to choose reference levels 0 dB, -1 dB, and -20 dB. So those are files containing a sine tone at those levels, 0, -1, and -20. Another signal that I want to grab here is SNR, which will be used for signal to noise ratio. And then further down here, I'm going to grab a frequency sweep, and this is a stepped frequency sweep, and I will grab full octave, sorry, 1/1 octave, -1 dB, and then finally the signal channel ID multi-channel. So once you've set all the parameters and the waveforms that you want to generate, you have to choose an output folder. By default, it goes to the user's My Documents folder, and I'm going to navigate to a folder on my C drive. Sure why that's so slow. Interesting. Oh, something went wrong with our little application there. All right. I'll just cancel reporting the problem to Microsoft. So let's try that again. So if I want to pick 2 channel, reference level 0, -1, -20, and channel ID multi-channel. I'll skip that sweep for now. See if I can browse to that folder. This looks a little more promising this time. And we want to go to, there's a folder called Wave and a subfolder called OLC Webinar. I choose the the folder, and then I just click Generate Waveforms. And the system generates those wave files as specified. Now, if I go to that folder that I just specified, you can see a collection of files here. And if I sort by the date created, you can see that these are the ones that I just created at the top. I have some other ones in there that we might use a little bit later. All right, so first I'm going to use this file called Channel ID Multichannel. And I have set up this program called Goldwave. It's an audio editor, recorder, and player, essentially. And I'm going to use it to play the files. This program is a third-party program, and it's quite inexpensive. You could also use a free program like Audacity if you want. This one costs about $50 US, I think, so it's quite cheap. But it's quite a good one for the price. All right, so just to make sure we have a signal here. And we can hear that coming through. So when I hit this play button here, the second one, it's going to play the signal continuously. I've set it up to wrap continuously. So let me generate the signal, and let's bring up the audio analyzer. And as you can see, let's turn down the volume so that's not so annoying. What I wanted to show you here, this is a special signal that we can use for that waveform verification step, or channel verification, to make sure we have the right connections. So this signal has a 1 kilohertz tone in channel 1, the blue trace, and a 2 kilohertz tone in channel 2. And then if you're testing a low frequency effects device like a subwoofer, we have frequencies of 51 hertz in channel 1 and 52 hertz in channel 2. So it's kind of a useful signal for that. And what we can do here is just look at the frequency result. And as you can see, I'm measuring 1K on channel 1, 2K on channel 2, and then I know that I have the right connections. I haven't made a mistake and swapped the cables, that sort of thing. All right, so let's go back to here. And now that I've verified the connections, I want to close that file. And next I want to open the reference level 0 dB. And this is a sine wave at 1 kilohertz, and it's at full scale. Now, let me just start this playing. And one thing I want to demonstrate here, just drag this over to the side. So in my FFT monitor, I wanted to point out, you can see I have my signal at 1K, and I have some harmonics at 2K and 3K and so on. But I have these very large sidebands, and they're down. If I switch this to dBV, you can see my main signal is at about 0, and these sidebands are at about -70. And those are artifacts of the signal that we're generating, unfortunately. So let's go back here, and let me load, instead of 0 dB, I'm going to load the same file, but at -1 dBFS. It's reference level -1. I'll just double click on it there. And if I generate this file, you'll notice that I still have the main signal, but I'm not getting nearly as large sidebands on the side here. Sometimes you have to be careful with these consumer connections. Sometimes you get a noisy connection, and you might have to fiddle with the connector a little bit. This is also an older laptop. There we go. So you see, I just fiddled with the connector on the outcome of the laptop, output of the laptop, and I cleaned up the spectrum quite a bit. So that's another way that we can verify connections. All right, so we have our 1 kilohertz sine wave at -1 dBFS, and once that's queued up and playing, we're ready to conduct some measurements. So the first of our basic 6 is level and gain. Let's have a look at that. Now, this is very simple. The system just measures the level of the incoming signal. So we can see we get 0.988 volts RMS on channel 1, 0.981 on channel 2. There are other results, gain, for example, but this is what we call kiboshed, because this measurement is unavailable when the output is non-external. So in this case, the analyzer measures the output from the DUT, but it doesn't know the level of the signal going into the DUT, and therefore it can't calculate the gain. That's the first of the basic 6. The next is THD plus N. Now in this case, the audio analyzer has some smarts built in. It's able to detect the frequency of the fundamental, and it's able to notch that out and to add up all of the noise and distortion. So we're seeing on channel 1 about 0.01% and 0.008 on channel 2. We can also express that in dB. So this first result is total harmonic distortion plus noise. We also have a variety of results. One is THD ratio. This looks at the harmonics alone without the noise, and you can see slightly better results when we exclude the noise. We have a noise ratio, which includes, it just looks at the noise in between the fundamental and the harmonics. And one of my favorites is the distortion product ratio. And this shows us a nice graph of the fundamental at 0 dB and all of the harmonics, H2, H3, H4, etc. And in the legend here, we have the frequencies of all of the harmonics. So that's kind of a nice display. All right, that's the second of our basic 6. I'm going to skip over signal to noise ratio for now and look at interchannel phase. And this one's very simple. So this measures the phase between the channels. So the reference channel here is channel 1. You have a choice of channel 1 or channel 2. We don't report a phase on the reference channel because it's in phase with itself. So we have a phase difference of minus 0.003 degrees here between channel 1 and channel 2. Pretty basic measurement. And then the next one I'd like to do is the crosstalk. Now the built-in measurement crosstalk one channel undriven is kiboshed, and this measurement requires the generator and the analyzer to work together. But we have another variant of it that can be used open loop, and it's called, what I did here is I clicked on the add measurement node in the sequencer, and the measurements are listed here as all, and there are quite a few of them, or they're broken out by basic. That's the basic 6, and then we have meters, single value results, we have sweeps, distortion, and crosstalk. So from the crosstalk, I want to choose crosstalk custom, and I'll click add and close. That adds the crosstalk custom measurement to the sequencer and makes it active. And the instruction here says, make sure that one output channel of your DUT is silent for this measurement. For example, turn off a single generator channel above, or disconnect or terminate one of the DUT inputs. So in my audio playback software here, I can simply turn off channel 2, and you'll see that I get a crosstalk measurement for channel 1 into channel 2 of minus 90 dB. Similarly, if I switch those and turn off channel 1, I get a crosstalk measurement on channel 1 of minus 92 dB. So that's how you do the crosstalk measurement in an open loop configuration. And there's also some crosstalk signals on that in that waveform generator utility that will generate just one channel at a time, and you can use those if you prefer. All right, and next we're going to look at signal to noise ratio. So this is one of those measurements that's not quite as easy to do in an open loop configuration because you have to measure the noise, turn off the generator, measure the signal, and then take the ratio between the two. So what we can do for this one, you may remember that I created a signal called SNR, and I'm going to load that signal now. It's called SNR 1 kilohertz. So this is a pure tone at 1 kilohertz. Unfortunately, it's at full scale, 0 dBFS. So we will be including those FFT sidebands in our measurement. But this is a signal that alternates from nothing, no signal at all, or no level, for 2 seconds, and then 2 seconds on and 2 seconds off, and so on. And if I start playing this signal, the analyzer should be able to just grab the signal and grab the noise. So we've measured a signal to noise ratio of about 88 dB. Let me just repeat that once or twice. Yeah, there we have about 88 again, and 88 again. So that's essentially how we measure the signal to noise ratio in an open loop configuration. All right, So just checking on this, we've covered level and gain, THD plus N, crosstalk, signal to noise ratio, and interchannel phase. So that's 5 of the basic six measurements that we talked about. So I want to skip back to the presentation for a minute, and we'll cover number 6. So, so the 6th one is frequency response, and this is a very important measurement in audio test. And I like to use a quote by Floyd Toole, who published this book in 2009. And his quote is, "Frequency response is the single most important aspect of the performance of any audio device. If it is wrong, nothing else matters." So that's just to emphasize how important it is. Now, typically for an electronic audio device, we like to have a very flat frequency response. This is the response of a little headphone amplifier that I've tested. And as you can see, we've put limits on it on the response from 20 hertz to 20 kilohertz. That's generally perceived to be the audible frequency range. And our limits are plus or minus 0.5 dB. So it's quite flat. Another way to express that is the deviation from flatness. So this is a single valued result. We call it a meter that expresses the flatness of the curve. And for this curve here, we've measured a deviation from flatness of plus or minus 0.27 dB, and we put a limit on that of plus or minus 0.5, just like we have here at minus 0.5 and plus 0.5. Now, the classic means of measuring frequency response is with what we call a stepped sine test. So we take a signal, a sine wave, and we start at 20 kilohertz, and we sweep to 20 hertz in a number of steps. And here we've defined a sweep with 31 points over that range, which is approximately 1/3 octave spacing. And we've defined the level and so on. So the analyzer for each step generates the sine tone, does the measurement, records the results, and then moves to the next step until it's done. Now this it's a classic measurement that we can always fall back on, but it does take quite a bit of time. And I've made a video of it here, and I've sped up the video by a factor of 5, just so we can go through it a little quicker. So let's run the video. So there you can see, I put a little timer on the screen here, and to do that sweep of 31 steps from 20 kilohertz to 20 hertz, it took 25 seconds. So, that's a good way to do things, but sometimes we like to go faster. And we have some tools for doing that, and we'll demonstrate how to use those in open loop test. Now, one of these is called a multitone analysis, and this uses a special signal called a multitone. And this signal has many, many sine waves combined together. So this is the FFT spectrum of such a signal. And as you can see, we have pure tones spaced logarithmically throughout the spectrum. And the system, once you acquire it, it does an FFT analysis and grabs the level of each of the peaks and then creates a frequency response graph. So this signal has 31 tones with 1/3 octave spacing from 20 hertz to 20 kilohertz. Now, the advantages of this type of test, first of all, it's very fast. You can acquire many, many results in 1 to 2 seconds. Results like frequency response, distortion, noise in the presence of signal, crosstalk, DC level, phase, and many more. It's also a very unique signal, which enables the analyzer to trigger on it without any false triggering. And we'll demonstrate that a little bit later during the demo. Some of the disadvantages. So this signal has what's called a higher crest factor than a traditional sine wave, which people like to use for testing. So a sine wave has a crest factor of 3 decibels. And multitone like this can have a crest factor of perhaps 10 dB, sometimes even higher, 15, 20 dB. It really depends on the density of the tones. So the disadvantage of that is the level at any one frequency is quite a bit less than the overall signal level. Another issue is that the distortion measured with this test is called total distortion plus noise. And the reason for that is the the harmonics are not just harmonics of any sine tone, but there's an interaction between the tones that causes what's called intermodulation distortion. So we can't tell if the distortion is due to harmonics or due to intermodulation, and we have to just call it total distortion plus noise. So some people don't like that as much because it's difficult to relate TD plus N to the more classic metric of total harmonic distortion plus noise. Now, just to give you an example of what this sounds like, I'll play it here. So it sounds a little bit like an organ playing a chord. It's more musical than a sine wave, and in some cases, that can be used to slip this signal into program material if you're in a broadcast application, for example. Another way of doing a fast frequency response measurement is with the log swept sine chirp. So this is as you can see, it's a sinusoid, but it increases continuously in frequency from low to high, and it's a logarithmically swept sine chirp. We're showing the frequency response here of a device swept in 0.35 seconds from 20 hertz to 20 kilohertz. So it's very, very fast. Now, another advantage of this type of measurement is we can use it for a measurement we call acoustic response. This measurement is ideal for loudspeakers and microphones because you can window out reflections if you do the measurement in an ordinary room. So without an anechoic chamber, you can do some level of frequency response measurements. So it's very useful for that. It also has rub and buzz detection, so it can be used to detect defects in loudspeakers and microphones that cause noises that can take away from the perception of audio quality. Another advantage to this device is it has a crest factor of 3 dB because it is really a sine wave that sweeps continuously. It returns the total harmonic distortion, which we can easily relate to a classic stepped sine sweep. And it's fast. It can produce many, many results in a matter of 1 or 2 seconds. One of the disadvantages of this measurement with some devices, they behave a little bit abnormally when they're stimulated with a chirp signal. So you can't always use it. It's great if you can. If you can't use it, you might have to fall back to a different technique, such as the step sine test or multitone, for example. To give you an idea of what that sounds like, I'll play this one a couple of times. This is a 0.35 second chirp from 20 hertz to 20 kilohertz. All right, so moving back to our demonstration, have the same setup. We have our device under test as a laptop. We're looking at its analog output. And all we're going to do is measure the frequency response using multitone and continuous sweep. So back in the audio analyzer software, I need to add a couple of measurements. And I'll just go from the All tab here. So the first, they're sorted alphabetically. So continuous sweep is the first. And the second one is multitone. I can just hold down the Control key, click on multitone. Now I've selected these two, and I click Add and Close. That will add the measurements to the sequencer. And all right, so first let's look at the multitone analyzer. Now this, in an open loop configuration, there are a number of predefined multitone signals in here that we can use, or we can create a new one, or if we've already created one, we can browse for a file. And that's what I'm going to do here. I've created one here called MT112020K. So it's 11 tones spaced from 20 hertz to 20 kilohertz. Now, if I open that signal, I can use the Edit button here to show what the signal looks like. So it's at 48 kilohertz. It has 9,600 samples. Sweeps from 20 hertz to 20K. It has 11 tones spaced logarithmically. And you can see here the tones and the phase of each. This shows the crest factor. And you might notice that there's an A channel and a B channel here. And the reason for using two channels is these are slightly different signals. So we've chosen to measure crosstalk with our multitone. And what the system does at certain frequencies, it generates slightly different frequencies in one channel than the other. So for example, our sixth tone here is 635 Hertz on channel A, and on channel B, it's 625 Hertz. So we have a difference of 10 Hertz, and the system is able to measure the crosstalk by having slightly different frequencies on the two tones. Now, once you've defined your waveform here, you can create a wave file of the signal. You can just choose the bit depth, 16 or 24, and the duration of the file. I've already generated the file, so I'm going to skip that step. And let's just go back to our audio analyzer and set it up. Sorry, go back to the device under test. So we'll close this signal. Oops, sorry. Close this signal and open my MT11 20 to 20K. And just to show you what it sounds like, I'll play it here. So that's about, that's 1 second. So I'm just going to park this over here, and the multi-tone analyzer can be run as a free run, which means there's no trigger, or we can choose to trigger on the level or on the signal. I'm going to choose the trigger on the signal, and once I do that, I can click the start button, and the system gives me a message here waiting for trigger, and it will sit here and wait until it gets that trigger. So let's go back to the DUT and play our signal. And as you can see, that measurement is completed, and we've measured the frequency response of our device in a very, very short time. Now, if we go to the very end here, we can see the acquired waveform, and you can see, you know, that's somewhat random looking, but it is, of course, periodic. If we look at the FFT spectrum, you can see the individual tones, and if I zoom in on some of our crosstalk tones, you can see a slight difference in frequencies on the two channels. So because, you know, on channel 1, there's a tone here, but there's no tone in channel 2, we can measure that value and report the crosstalk. So that's kind of a cool feature. We have a huge variety of results here. We have the frequency shift. Now this accounts for the sample rate difference between the device under test and the original signal. There always will be some slight difference. We can measure the DC level, the signal to noise ratio, the noise level, the noise density spectrum, and so on. So really a large variety of results that you can use. Now, something else I wanted to point out, I mentioned that this signal is quite good for triggering on. So just to demonstrate that, I'm going to load a signal that has music with the multi-tone embedded into it. So let me choose this track here. And you might notice that, you know, this is kind of musical looking, and when I get to this part, it's very uniform. That's the multi-tone, and that occurs at about 15.5 seconds. So let me just park this on the screen, and I'll click start here. So again, it's waiting for trigger. Now, you know, this could be an application where you're testing a broadcast network and you're playing music for hours and hours all day long, and you want to slip in a multi-tone that's only 1 second long in the middle of the program material. So let's see what that looks like. So as you can see, the system is very robust against false triggering, and we've managed to acquire that multi-tone in the midst of all of that music that's going on. All right, next I'm going to look at the continuous sweep measurement. We loaded that earlier here, and when we're in this configuration where the generator is set to none external, the system already knows that it's an open loop configuration. So the open loop checkbox here is checked by default. We can't uncheck it in this configuration. The other thing that happens is we get 2 buttons instead of 1. There's a generate button and an analyze button. The generate button is used to create a wave file of the signal, and the analyze button is used to acquire it and analyze it. So looking at our settings, the default sample rate is 48K. That's what I want to use. The number of channels is 2. There's a pilot tone, so the system has to trigger on a pilot tone, and the pilot tone is also used to calculate the frequency error between the DUT and the original signal. The sweep is from 20 to 20K. That's great. Pilot tone is at -20. The sweep default level is -20 dBFS. I'm going to change that to -1. And then I have a pilot tone of 200 milliseconds, silence of 100. The only thing I'm going to change here is the sweep length. Change that to 2 seconds, and I'm ready to generate the signal. I click generate, and I get a prompt to save the WAV file. So I'm going to choose, just browse to my desktop, and I'm going to give it a name, MyChirp, and replace the file if it exists, and it will be multi-channel, stereo, and 24 bits of depth. So let me save that. And now if I go to my desktop, I can see the MyChirp file. I'm going to copy that, go over here to the device under test, and paste that in this folder. And now I can just load that file. So I want to load mychirp.wav, and here's what it looks like. All right, so go back to the analyzer. Now, if we click Analyze, you'll see it says Operation in Progress, Acquisition 1 of 1, waiting for the 1 kilohertz pilot tone. So it's got some timeout built in, but it's going to wait until it gets the pilot tone. And if I play, it should all trigger and do the analysis. And I did get a warning message here, so there's a step that I forgot. And you'll notice down here at the bottom, the input range is set to 310 millivolts. And what's happening, that's a feature of our analyzers. It uses a technique called auto ranging. So it keeps the analyzer in the lowest range until it sees a higher signal. And with the chirp measurement, it has to be all in the same range. So I have to turn off auto ranging here, set my input to something like 2 volts. It'll take the next higher range of 2.5. And this should work now because it's got enough range. So it's still waiting for the pilot tone. And there we have the analysis. So we have the RMS level. I can calculate the gain in this result because the analyzer knows the characteristics of the generated signal. We have a relative level result, a deviation from flatness. We have the THD ratio. We also have the acquired waveform and lots of different audio quality metrics there. All right, so that's a fast way to do frequency response measurements. So moving back to the presentation now, I'm going to carry on. And the next thing I want to cover is the open loop test procedure for a recording device, or the recording function of a device. So here the DUT might be a media recorder or a audio recorder, PC sound card, anything that records essentially. So we configure the generator, we configure the device under test, and we start the recording. We generate the signal on the analyzer. We stop the recording when the signal has been acquired. We save a file and transfer it to the PC running the APX software. We may have to decode it, and then we analyze the file with the APX software. For an acoustic device, there's a couple of extra steps involved. So here we might be stimulating the microphone of a smartphone, for example, with a mouth simulator, a small powered speaker. So we configure the generator. Another step is we EQ the mouth simulator. We'll talk about that in the next slide. We configure the DUT and start the recording. We generate the signal, stop when it's complete, transfer the recorded file to the PC and analyze it. And there's an additional step here. We may window the impulse response or the energy time curve to window out reflections, and then we get the analyzed signal. Now I mentioned equalizing the mouth simulator. Mouth simulator, this one looks like this. This is made by our sister company, Gras Sound and Vibration. And it's a small powered speaker with a small opening that approximates the mouth opening of an average person. There's one built into the head of this head and torso simulator. Now, like any loudspeaker, this does not have a flat frequency response. So you can see I have a variation from peak to trough here of more than 20 decibels from 100 hertz to 8 kilohertz, the speech range. So to play these speech signals correctly, I need to equalize that to have a flat response. Now, the way that you do that, you can put a microphone at a special point in front of the mouth simulator called the mouth reference point. You calibrate the microphone, you measure the frequency response of the device, and then you can export it and import it as an inverted fashion. And if you equalize this curve with an inverted version of this curve, you'll get a flat response. And that's how we equalize the mouth simulator to have a flat response. All right, so in our second demonstration here, we're going to look at the recording function of a laptop sound card. So in this case, I'm using the analog output as the generator. I'm connected to the mouth simulator, the powered speaker. I'm going to play a speech stimulus, and I'm going to record it on the PC, save a WAV file, and move it back to the analyzer. And then I'm going to use a transfer function analysis to find the frequency response between the acquired signal, the recorded signal, and the original file, the original speech. So let's go and set up our analyzer. Another thing I want to do here is I'm going to, instead of opening a file, I'm going to create a new file, and it's set up to record a stereo file at 44.1 kilohertz for 20 seconds. So we'll just check if we're ready to record here, make a little bit of noise. Yeah, that seems to be working. So I will select all and get ready to record over top of that. And then we get our analyzer prepared to generate that speech signal. So to do this, I'm just going to load a project file, which is all set up for this. If I pick File, Recent Projects, you can see a project file that I've saved already. And this is set up to generate my speech file. So I've gone through the steps of calibrating the microphone and the mouth simulator and equalizing the mouth to have a flat response. Didn't really want to go into those details today. All right, so just to see, this is a special signal called the International Speech Test Signal, and it contains speech in 6 different languages all mixed together randomly. So let me go ahead and generate that. So what I'm doing here is I'm measuring the RMS level every second, and then I'm adding up the overall RMS level, and my target level is about 89 decibels of sound pressure level at the mouth reference point of the device. So once I've got the signal ready to play, I can just click here, the record button, and then generate the signal. All right, so that's finished recording, and just to verify I have a signal. So the next step here is I would save this, a WAV file of the signal. I would copy it to the PC running APX. And then what I want to do is go to the second signal path in my project. And in this signal path, let's just have a look at the signal path setup. So I've set the output to non-external, and I've set the input connector to file digital units. And that means instead of looking for a signal at an input connector, the analyzer is going to pull the audio from a file. So I've set up my transfer function measurement here. And what I've done is I've chosen the file here, and the file it's called .recorded.wave. So that's a file that I recorded from this melt simulator on the laptop previously. It's one I would have transferred over in the last step. And then for the reference, I'm choosing the original version of that wave file that was generated by the generator. And if we look at the acquired waveform here, we can see the analysis proceed. So it's matching on the signal and then going through and doing the analysis. Now you can see this is 14 seconds of analysis roughly, and it's able to analyze the signal much quicker because the audio is coming from a file rather than from sampled audio, so it can proceed quicker. So I have the acquired waveform, I have the reference waveform. This is a result called cross correlation, used to find the delay between the two signals. This delay measures the amount of time between the signals, about 1.5 seconds. That delay is removed. We then look at the FFT spectrum of the input signal. You'll notice that it falls off pretty rapidly at 8 kilohertz. That's an indication that the microphone is internally being sampled at 16 kilohertz, even though the wave file is at 44.1 kilohertz. Next, I have the FFT spectrum of the reference signal. And finally, the frequency response function magnitude, that's the ratio of the acquired and the original. This is quite noisy. This is not a very good acoustic environment. So I can apply a little bit of smoothing and just smooth out that result and get a nice measurement of the transfer function of the laptop microphone inside this room. All right. So that's the end of that demo. And just for review, just a quick review. So we've talked about open loop measurements, what some of the challenges are, and some of the devices that require open loop testing. We've reviewed the basic 6 audio quality tests. We've done a demo of a playback device test open loop, and also a demo of a recording device test acoustic, and also done open loop. And at this point, we're ready to take any questions you might have.
All right, great. Thanks, Joe. I currently don't have any questions in the queue, so everyone, as a reminder, you can submit your question via the chat function on your screen. While we wait for some questions, I'll go ahead and take a moment to tell you about some resources that are available to you. If you go to our website, www.ap.com, we have a myriad of audio test assets available for you. This includes application notes, data sheets, and many other downloads that you can access for free. So if you're not registered on ap.com as a user, we recommend that you go ahead and do so you stay up to date on the latest in audio test. And you can also visit the AP blog for posts about audio test and measurement. We regularly publish content that goes over measurements, best practices, tips and tricks. Yeah, excellent. Thanks, Joe. And Joe previously mentioned THD plus N in this webinar. He also wrote a blog post on THD plus N, so you can learn more about that measurement on our website. And with that, Joe, I do not have any questions that have come through, so I think it's time to go ahead and wrap up. And I just got a question came through that asks, can I access this recording of the session later? Yes, there will be a recording that will be available early next week, so be sure to check your email, and we will share the recording of this session with all registered attendees. All right. Looks like that's all for this evening. Thank you everyone for joining. We're really excited to present this info to you. And if you have any questions about your application, feel free to reach out to our sales team, sales@ap.com, or also feel free to contact our tech support team, techsupport@ap.com, to discuss your application. So thank you everyone again for your time, and I hope you have a great day or great evening. Joe, anything else you want to add?
No, just thanks everyone for attending, and thank you, Paige, for being a great producer again.
Thank you. Thank you. Thanks, everyone. Take care.